Computers excel at finding patterns in data. Humans excel at creating libraries that help computers find patterns in data. Scikit-Learn is one such library, a collection of tools that transform data into knowledge through the power of machine learning. Whether you seek to classify, regress, or cluster, Scikit-Learn stands ready to assist. Scikit-Learn is a machine learning library that transforms raw data into actionable predictions. Unlike traditional programming where humans write explicit instructions, Scikit-Learn enables machines to derive their own rules from data. Among its many capabilities, the library's most commonly used tools are for classification, sorting items into categories; regression, predicting numerical values; clustering, grouping similar items; dimensionality reduction, simplifying complex data. Consider classification. A traditional program might use if statements to categorize data. But what if you have thousands of features, millions of examples? The logic would collapse under its own weight. Instead, Scikit-Learn employs algorithms that learn patterns from data. These algorithms include random forests, support vector machines, neural networks, and k-nearest neighbors. These algorithms follow strict design principles but simplify the use of machine learning. For example, all estimators share the same interface. All parameters exist as public attributes, allowing full inspection of the learning process. Pipelines compose multi-step workflows into efficient modular sequences. Even beginners can achieve impressive results thanks to sensible default configurations. Finally, Scikit-Learn values computational efficiency. It converts your data into NumPy arrays, dense grids of numbers optimized for calculation. The documentation is thorough, the examples are practical, and the error messages are illuminating. We begin with a classic classification example: the 1936 iris flower dataset. When botanist Edgar Anderson collected these flower measurements, he undoubtedly knew they would one day be invaluable for our machine learning needs. First, we load our floral specimens, a dataset consisting of 4 measurements from each flower: sepal length, sepal width, petal length, and petal width. Each measurement is in centimeters. Let us examine a few. Here we display measurements from 3 different iris flowers. Run. Notice how the features differ between species. The setosa has a small petal length and width, while the virginica's petals are substantially larger. These patterns are precisely what our model will learn to recognize. But before we train our classifier, we must first tidy up our features. When data are normally distributed, it is standard practice to normalize the data. In other words, transform the values so the mean is 0 and the variance is 1. In Scikit-Learn, the StandardScaler will do this for us. And one more thing must be done before we proceed. We must divide our data into training and testing sets. It would be most unfortunate to test our model on the same data used for training, a classic example of overfitting. Now, let us train a logistic regression model. Despite its name, this algorithm performs classification, not regression. The nomenclature is admittedly suboptimal. How good is our model? One way to check is by printing the accuracy. Run. Pretty good. Our model appears to be performing well, but raw accuracy can be deceptive. A deeper analysis is required. For classifiers, you want to find the confusion matrix. The confusion matrix organizes predictions into a grid where each row represents the true class, each column represents the predicted class, and the diagonal entries indicate correctly classified examples. Off-diagonal entries reveal misclassifications between specific classes. Run. Each row represents an actual species, while each column shows what our model predicted. Perfect classification would result in numbers appearing only on the diagonal. As you can see, the confusion matrix is a diagonal matrix. and our accuracy is 100%. While this may look impressive, it tells us something important about the iris dataset. The classes are easy to separate. Real-world data is rarely this clean. Models will face noise, ambiguity, and overlapping features. Perfect results here are a sign that the dataset is simple, not that the model is infallible. The confusion matrix showed us that our model can separate the classes perfectly. But this only tells us what the model does, not how it does it. To peek inside our classifier's decision-making process, let us examine which features it relies on most. The coefficients tell an interesting story. Run. Petal length and width appear to be the most influential features, a fact that would take a botanist significantly longer to determine. To understand why, let us visualize how these measurements relate to each other. Run. A pair plot shows us every possible combination of our 4 measurements, with each feature plotted against every other feature. In the plots where petal measurements are involved, notice how cleanly the species separate into distinct clusters. This visual confirmation explains why our model relies so heavily on petal measurements for classification. For a final test, let us predict the species of a new iris specimen. We will input measurements from a flower. Remember that any input measurements must undergo the same scaling transformation as our training data. Run. The model predicts this is an iris setosa. These measurements, particularly the small petal size, are characteristic of the setosa species. This confirms what we learned about feature importance. Now that we have classified the flowers, take some time to smell them. Ah. Next, we proceed to a more human example. Handwriting, specifically the digits dataset. This is a simplified version of the famous MNIST dataset, perfect for learning the basics of image classification. Scikit-Learn comes with a method for loading this dataset. This dataset consists of 1,797 grayscale images of handwritten digits from 0 to 9. Each image is compressed into an 8x8 pixel grid. That is 64 pixels per digit. Let us confirm the shape of our dataset. Run. As we can see, 1,797 samples, each with 64 features. Let us examine one digit from our dataset to see firsthand what we are asking our machine to learn. Run. To our eyes, it forms a number. To our model, it is merely a point in 64-dimensional space. Perspective is everything. While humans excel at reading digits, we must help our algorithm understand, for instance, that a tilted 7 is still a 7. Before training, we scale our data so all features contribute equally to the model. Our data is now ready. Commence training. For this task, we will use a support vector machine, or SVM. Despite its name, it is not a physical machine, but a mathematical method that finds optimal boundaries between classes. In our case, it will create boundaries in 64-dimensional space to separate different digits. Scikit-Learn uses SVC for support vector classification and SVR for support vector regression, much more specific than SVM. The SVM requires careful tuning of its parameters. The C parameter controls the trade-off between decision boundary simplicity and training accuracy. A low value creates soft boundaries, while a high value enforces strict separation. Let us see how well our model performs. Run. An accuracy of 98%. Impressive. But what kinds of mistakes are lurking in that 2%? Time to investigate where our model succeeds and where it requires optimization. A confusion matrix shall be our diagnostic tool. Run. Observe. Each row represents the true digit, while each column displays our model's prediction. A perfect model would show values exclusively along the diagonal. Note the sporadic off-diagonal elements. These are the few occasional misclassifications. Let us proceed to examine our precision and recall metrics. These can be found in the classification report. Run. Precision and recall provide complementary measures of our model's performance. Precision examines our model's predictions. Of all instances where it proclaimed a certain digit, what fraction were correct? Recall examines our model's ability to detect. Of all instances of a certain digit, what fraction were successfully identified? In machine learning, precision and recall represent a genuine trade-off. As you adjust model parameters to increase one, you often decrease the other. The classic example is that you can get perfect recall by predicting every instance as positive. You will catch all true positives, but your precision will be terrible. Now, let us observe specific instances of confusion. Run. Here are several examples of misclassification. They may even pose a challenge to your eyeballs. Having analyzed our model's performance, let us explore methods of enhancement. One powerful technique is grid search, an automated way to systematically test different values for each of our model parameters. For each parameter, we provide a set of values we want to try. Grid search will then test every possible combination of these values to find which set produces the best results. Scikit-Learn also gives you a pipeline tool for controlling the different stages of a machine learning problem. First, scaling our data. Second, reducing dimensions with principal component analysis, also known as PCA. And third, classification with a support vector machine. Pipelines help us organize these steps into a single cohesive workflow. Let us set up our parameter grid. For PCA, we will test different numbers of components from 20, 30, 40, and 50 dimensions. For our SVM, we will test 3 different values of C, 0.1, 1, and 10. The C parameter controls how strictly we enforce our decision boundaries. We will also test both the RBF and polynomial kernels, which determine how our SVM transforms the data. For gamma, we will test 2 approaches, scale and auto. In total, this creates 48 different combinations to evaluate. 4 PCA components times 3 C values times 2 kernel types times 2 gamma settings. Next, we pass these parameters and our pipeline into a GridSearchCV object. CV stands for cross-validation. We then specify which data to train with. And once training is over, we will print some performance metrics. Run. The grid search has found our optimal parameters. When used, these parameters achieve an impressive cross-validation score. Now for the pièce de résistance. How effective was PCA? Our original data had 64 dimensions, 1 for each pixel. PCA reduced this to just 40 dimensions while preserving 95% of the variance in our data. We have significantly simplified our model without sacrificing much information. Think of PCA as compressing an image. We have removed the noise while keeping the essential patterns that make each digit distinct. This not only makes our model faster, but often helps prevent overfitting by focusing on the most important features. Remember, in machine learning, simpler solutions that generalize well are often preferable to complex ones that might be slightly more accurate on training data. It is about finding that sweet spot between complexity and performance. Scikit-Learn strikes a perfect balance between simplicity and power. consistent APIs, automated parameter tuning, built-in validation tools. With all this and more, Scikit lets you focus on solving problems rather than writing boilerplate code. While deep learning frameworks may grab headlines, Scikit-Learn remains the trusted workhorse of machine learning.